So we are going to start this session. Is related with AI, this artificial intelligence, something that you are speaking every day, everywhere, in every place today. Of course, there will be some presentations about the application of the AI in several fields of the pulping, paper, forest, and I think that we will have a good moment to hear these gentlemen that are here. I start to introduce them. I'll introduce myself first. My name is Carlos Brás. I'm working in the Navigator in Portugal for lots of years. We'll start with Filipe Louro, who is here on my left side. He holds a master's degree in ecology and geospatial data science, something very interesting. He has 5 years of experience in eucalyptus ecophysiology research, specialized in hydric stress and biometry. For the last 5 years, he has been part of the Navigator company's forestry innovation and development team, focusing on the digitalization in forest management, remote sensing, forest inventory, and forestry expansion programs. The second presentation will be done by Mr. Juha Rintala. He holds a master's degree in chemical engineering and has an extensive experience in pulp and paper chemicals industry. He has served in key roles across technical sales support, product line management, marketing, and new product development. He is committed to driving operational excellence and sustainability, and he helps customers enhance production line performance by optimizing Solani's chemical solutions through advanced digital technologies and predictive analytics. On my right side is Mr. Grant Downham. You will have the opportunity to present the third subject. He works for BTG, a Foyt company, as is here, as the Global Tissue Market Manager, and holds a BSc degree in Chemistry and Applied Chemistry, and a Bachelor of Technology degree in Pulp and Paper. Grant has 28 years of experience as a supplier to the paper and tissue industry, and has focused on the tissue sector most of his career, holding numerous technical specialists, business development, sales management, leadership, and market management roles in this regard. So we are not going to lose more time. Please, Filipe, it's your turn.
So good morning, thank you, and thanks to Sherman for the introduction. So our work focused on detection of forestry or forest harvests and fire detection. And the context is that Portugal has approximately 69 to 70% of forest area in the mainland. However, most of those holdings are very small, especially on the northern region. Most of them are under 10 hectares, and about a fourth are 100 to 2 hectares. So these small dimensions imply very big difficulties in monitoring, and usually the lack of management will lead to reduce the productivities and also abandonment by the property owners. So usually when we need to detect land use and land cover changes with satellite imagery, most people use the Landsat time series, which is an American program. It's been online since the 1970s, and it's been the golden standard for satellite imagery. However, people usually do. You get image A, you get image B, you try to find the differences between them. However, since 2017, we have the European program, the Sentinel-2, which has a much better spatial resolution, so 10 meters instead of 30, and also a time of revisit way shorter, 5 days instead of 8 days. So this allows us to not only see, and since we have the time series and we have higher processing power nowadays, we can, instead of just checking image B and image A and image B and see the difference, we can actually study the whole trend and try to find the changes. For this work, we used an algorithm, which is the CCDC, the Continuous Change Detection and Classification. This algorithm, for each pixel, through the whole time series, will try to apply, to fit an harmonic regression using a lasso. And since we have the harmonic regression, we can study the global tendencies and also the seasonal tendencies of each pixel. And we can also apply, for instance, a chi-square test to every new measurement and see if the new value is as to be expected or not. And if it's not, we can signal a break or a change. So as I said, usually it's Landsat that's used for this kind of algorithms. However, in 2024, we had the first try with Sentinel-2 and in Portugal. So this parameterization uses the NDVI, the vegetation index, and tries to see if the reduction or the change in the vegetation index is enough to signal a harvest or a fire. So with this work, we tried to validate those with real data from the Navigator company. So we selected 300 eucalyptus stands from the Navigator company, and for the window of 2021 to 2023, we collected all the harvesting operations, all the other operations, and also all the stands that were affected by forest fires. And we classified them using the algorithm, the CCDC, and we classified them as true positives if the detection of the algorithm matches the historical data, at least 80% of the area, and at a maximum of 60 days. We have the true negatives if there's no harvest and there's no detection, and false positives and false negatives, however, they are mismatched. So this is one prime example of a true positive that we got from a harvest. So this is a false color image. The red is infrared, so it should be vegetation. And as you can see in black, the Navigator stand, and then in blue, the detection from the algorithm, and it actually fits like a glove, so it's really good for us. Here we have a fire example. So this is a Navigator stand that was affected by the fire of Admira in 2023. And as you can see in red, the fire actually stopped around there because there was no more to burn, but it was correctly detected. This is actually one of the false positives we got with our work. This is actually a young stand which the undergrowth was cleaned with a tractor. So there was some vegetation that was cleaned, and our algorithm detected those changes. And as you can see, it's not as clean, but there are some detections. So how do we evaluate this? We start by evaluating the overall accuracy, which is how many were correctly detected over the whole stand. However, those kinds of metrics for this type of work does usually influence the results. They skew it positively because there are usually a large number of true negatives that are correctly identified. So it's better to use an F1 score. And in this case, we calculated the commission and omission, so the errors that the algorithm detected that it shouldn't have, and the ones the algorithm omitted. So we find here the results by stand and by area. As you can see, they are really good. The accuracy around 90. The F1 score is also in the mid-80s, which is really good. And I'd like you to look at the omission and commission and see. We chose to have this algorithm as sensitive as possible. So we wanted the omission to be reduced to 0 or as close to 0 as possible. And that, of course, is kind of a seesaw with the commission. So the algorithm is really sensitive. It will detect things that it shouldn't. However, it will not miss stuff. However, the false positives we find, if we go and check them, most of them are actually from anthropogenic intervention. So if it's from other operations like clearings, like site preparation for new plantations, there were only 3 cases that weren't that, and that took us by surprise, that were sudden increases in vegetation. We weren't expecting that. Those 3 cases were periods of a long drought and then sudden rains, and that led to a huge boom in vegetation. And we got 3 cases where we detected those curves going up. That, of course, is easy to fix, and we already fixed those to future iterations. So we have 2 questions to answer. First of all, does the area matter? We found out that it didn't. So most of the smaller stands that we studied that had harvests were detected, so there was no problem there. And even the smallest stand that wasn't detected was around 20 hectares, so it shouldn't have impacted it. Second, does time matter? As you can see, about half of the harvests we detected in 6 days. So it should have been 1 pass of the satellite. So we were really happy with that. And about 80% in 19 days. So it should have been around 3 to 4 passes of the satellite. That delta is usually explained by cloud coverage, especially in the rainy season. We usually have weeks, if not even months, of images that we can't use that are masked because of the clouds. And that's usually why we have some stragglers along the way. A few conclusions. The product seems adequate and it closely matches the reference data. And the Sentinel's time series seems to be useful for this kind of work. Although it is still short, as I said, it started in 2017 and we were working with 21 to 23, so 6 years. We expect that as the time series starts to grow and to be longer, we should have better results. There's also a warning. Our reference data, even though we had very small stands, the Navigator's small stands are not Portugal's small stands. Portuguese and other property owners' small stands are usually way smaller than ours. So if there are, especially narrow, if there are narrow stands, the algorithm might not be able to catch those. The algorithm this tool should enable a forest manager to monitor and to check if their own stands are being harvested, when they are being harvested, and how, and to check productivity of the harvesting team. They might enable a commercial agent to monitor other neighboring stands and to obtain some intelligence and even competitive advantage. And we think that it can also be useful for legal compliance with the European Union deforestation regulation, since it might help us to carry out due diligence. Thank you.
The next presentation is called Autonomous Control of GRAMMAGE in Fine Paper, Moving to Paper Industry 4.0. So Juha Rintala will be the speaker.
Okay. Morning. Thank you for the organizing committee and the chairman to give nice presentation. I give you a little bit more details of my background. As said, my background is in chemical engineering. I have been working with the industry already quite a long time, especially on the paper chemical side. I have been kind of different positions. These give me quite good understanding of the current situation, what the industry is facing, as we yesterday heard in the first session. The outlook at the moment for pulp and paper here in the European side is a little bit challenging, and maybe these challenging times will continue to do so in the near future as well. But nevertheless, let's try to stay positive, and maybe this is really the time now when there are challenging times to look for different kind of ways how to help paper makers to overcome the situation. And you might wonder why me as a chemical engineer and at the company that I'm representing is speaking about digitalization or AI or these kind of modern technologies. Well, where's the catch? Hoping that during the presentation you will find the connection when I'll go through my slides here. But kind of aim of the project that I'm presenting is how to help graphical paper makers to optimize the fiber uses. Everybody understand that this is expensive part of raw material, and any ways to reduce the consumption of paper without jeopardizing the key quality parameters of the paper is welcomed. Modern copy paper machine nowadays, let's say how things are done in the control room is that the operators need to kind of all the time be aware that what are the porosity values, thickness, roughness, and based on the laboratory measurements which are done from the finished reel after it has been produced, somebody goes and take a sample, took it to the lab makes the analysis and gives the results, and then operators will make the adjustments. So there's a lot of information, a lot of interaction in between the key parameters, and then they need to think about the filler ratio, fiber ratio, basis weight, refining, and calendar load, for example. So pretty complex thinking process. Also good to understand that operators tend to have a little bit different background. Some of them are really experienced, some of them are new, so there's a lot of variation how they tend to process this information and act accordingly. So this gives kind of good information that when operators are in charge of decision making, so there might be a lot of variation. So thinking if there would be a possibility to have a system where the modern technology is doing the predictions of these key parameters for the paper, and then giving out an information to operators to do the actions, or the system automatically adjusting these parameters. So yeah, that was kind of the focus, and now to the catch itself. So as a company, we are biggest chemical supplier to the pulp, paper making industry. So we want to utilize this deep expertise what we have within chemistry and chemicals. Combine this to the process understanding, and then utilize the modern AI technology in cloud environment and do these kind of predictions. And that's why that's the catch, that how we deliver value to our customers by giving this understanding or utilizing this chemistry expertise together with modern technology. Especially on choosing the data tags for the modeling part, this is the key thing. There are a lot of, let's say, companies that can provide similar kind of solutions, but then when they are looking for the data tags, they might think that, okay, let's use as much of data what the system is producing, and easily there are thousands of data tags continuously, real time. So let's take a big chunk of the data and utilize that. When basically you don't need to do, you can select tailor-made or tailor-pick the really tags that are related to this prediction on certain quality values. And typically, we are talking about few hundreds of data tags, which is pretty much, let's say, a small portion of all the tags what the system is providing. So we focus on certain key things. Of course, we look for the key chemistry parameters if there are. If there are not, we would have the possibility to utilize our analyzer fleet, so we would get the critical information, but then we are also looking for the key mechanical parameters from the process, like flows, like tank levels, like fiber usage, and so on and so on. So altogether, around 200 data tags, only what is needed. The reason basically for this is that if you are using too much data tags, you make the system very, very complex. And it gives you a kind of, it goes into the risk that your prediction model is not working too well or requires a lot of training, or there's like risk for kind of false information. So that's why if you focus on limited amount of data tags, then kind of the success for reliable measurements or predictions are there. So that's why, okay, focus on the really needed data tags with the careful selection. The other thing is that modeling challenges. So everybody understands, if you are working on a paper industry, that the system is very complex, very dynamic, and I'm not only speaking about the mechanical dynamics in the system, but also chemical fluctuation dynamics. So if you think about, okay, let's take into account certain tags, how we make sure that we also understand the chemistry changes. And this is kind of now the key in our modeling system. So we have been able to choose to use these technologies that takes into account both mechanical and chemical changes, fluctuations, dynamics. And just to give you an example on situation, if you have a integrated mill, something happens on the pulp mill side. Let's say that the last washers, they fail, or one of them. So there's a little bit impurities coming together with the pulp. You don't see this on the pulp mill, on the paper machine immediately, because there is a tank or tower in between giving like 20 hours buffer time. Slowly, then after 20 hours, this comes to the machine. Okay, you can see it with the conductivity, you might see it in turbidity measurements, only if you understand the meaning of those, or only if there is somebody following these measurements. Typically, maybe not, but with our system, for sure. And then it will cause runnability issues, it will cause some interaction with chemistry, maybe the retention is a little bit failing, water removal, consistencies, quality. And the time dependency on all of these are totally different. Like the residence time in the tank, and then when it goes to the short circulation, chemical reaction, and they are like happening immediately. So you can imagine that having a system that understands these kind of correlations are critical. Okay, so we were happy to work with our customer. Very modern paper machine, copy paper machine, operates in Middle East. I would say the most modern copy paper machine, started up less than 10 years ago. Solenis was selected to be the key supplier for the chemicals for the startup, and we are still there. And therefore, let's say we had a nice possibility last year to present optics for the customer and started to discuss, would there be any possibilities to help you guys to operate the system and look for opportunities to lower the operational cost. You can imagine the situation today, declining demand for the copy paper market, so everybody's looking for ways to reduce the cost. So we got an idea that what if we would be able to do exactly what was the goal of what I explained in the earlier. Hey, focus on the quality, predict the quality, and create a system that automatically adjusts these parameters, GSM, filler, calendar load, refiner load, based on predictions. The production team at the mill was really eager, motivated, committed, which is a key thing. So we were able to create a connection, secure connection, because all the modelings, calculations happen in cloud environment. So, and within only 1-2 months, we were able to demonstrate the first predictions. And then February, earlier this year, we went for full control. Okay, in between last fall, this February, there were a lot of trials done, open loop, closed loop, controlled manner. So we didn't jump into the control system immediately, but of course there was some kind of trials done and you know, together with the production team. So you show here a picture on the screen what we have in the control room, and then the dashboard. You can see that there are the predictions. There are like also showing that what is the system proposing for the set point. The system was communicating with the Valmet DNA, so it was fully integrated and connected, and therefore our system was setting the set point for these parameters instead of operators. Operators has always possibility to take it on manual and do it how they have been doing in the past, but so far this has been on full control from the beginning of the trial. Oh, there it comes. So the results. As you can see, we were able to heavily reduce the variation of these key quality parameters. So that was the first signals, and these results are from the first months of the trial, when the system was full in control. So we saw heavy reduction in variation, which is coming when the machine or the system is making the decision, small steps. And then the best kind of indication that we were able to reach the goal was that you can see that the fiber reduction is in between 1% and 2%. And maybe you are better to describe the benefit or the economical benefit, what this means for a customer, but clear indication that the system works like it has been designed to do. So can't say that the customer is happy, and that's why we still are in full control, and we are still working with the mill team to kind of improve the predictions and improve the small corrective actions what our system is proposing. So there is a certain algorithm behind. So based on all of these 4 predictions, there's an algorithm calculating what is the action for the calendar load, filler load, refiner load, what is needed to be done. So we are on the right path at the moment. It looks like that this is something what we are able to reach, at least with this customer, and let's see what are the possibilities for the future. A couple of words of the optics system. So as you can see, we have been working with the system already for years, many years. So there is a certain roadmap where from we started and where we want to go. We are pretty much in the middle or a little bit over on the middle of the road. And now we are focusing on OEE improvements, sustainability improvements, and this kind of example on this copy paper machine really nicely explains the, am I out of the time? No, not yet. Okay, so, but that's it, like that was my last slide, so I thank you a lot, and if there's any questions, I'm happy to ask, to answer.
So, we'll make a question.
Okay, okay, great.
Thank you very much.
Thank you.
Sorry for that. It's okay, we have to keep this going. Okay, now it's time to Grant to present
That's correct?
Yep.
a theme related to vibration as a tool to understand the interaction at the creping blade. So we are now moving to tissue industry.
Yeah.
Please, go ahead.
All right. Well, thanks for the opportunity. Enjoying being in Portugal, and hope you get some good information out of this presentation. As mentioned, looking at vibration and help us understanding what's happening at the creping blade. So just in that regard, tissue is very different from paper making just from the fact of the creping process. It's pretty much like driving a sheet into a creping blade at the speeds you do at highway driving. So pretty much like driving a car into a brick wall, all right? And there's some key factors that dictate that impact and what's happening at the blade. There's the coating thickness and adhesion and hardness, and then your blade material and geometry. Those are key factors that determine what happens at the blade, and ultimately that's going to drive your sheet productivity and quality, and very much related to bulk, softness, and stretch. Related to the coating thickness and adhesion and hardness, there's other factors that influence it. Your obviously Yankee temperature, hood, things that drive that coating thickness and hardness, as well as your natural coating. So it's not just what you spray on it, but the coating ultimately influenced by it. And then we believe that vibration can play an important part in understanding those interactions, and we're going to talk about that through some theory and then some case histories on that. And ultimately try and show how we can drive the right productivity and quality from understanding that better. So when you talk about coating hardness and thickness, you can get a hard heavy coating where the blade rides on top of, and you can get things like pinholes, picking, and chatter when it's not optimal. You can get a coating that doesn't set up before the nip, so that it just sticks the sheet to the dryer. It obviously goes in the felt, and then the blade actually can't get under that coating, barely gets under the sheet, and you end up with fibrous chatter, picking, bypassing. I view that as very much as like when you got an egg on a frying pan and the spatula can't get it off because there's nothing in between it. And obviously vibration can pick these things up. Then you get a soft coating that can be stripped off the dryer. You get hard blade wear, no Yankee protection, just sliding across. But then as the blade wears, you can get to the other side of it where there's fibrous on the chatter and just picking and that on the dryer. And we get to a more doctoral coating that we believe that we call it the blade swims in the coating. So it's in the optimal, it's not directly against the dryer, but it's in the coating itself and gliding in it. So obviously vibration and things like that would be optimal, and that shows good blade and Yankee protection and ultimately your best quality, and that's through the adhesion. We'll talk about that on the next slide. So we have your coating thickness and hardness is going to affect how that blade penetrates into the coating, and you have, so it's going to affect the adhesion and ultimately the force of the impact at that tip. That's because there's an optimum adhesion gradient through the coating. Obviously, if you're right up against the dryer, you don't have a lot of adhesion, and if you're riding right on top of a hard, heavy coating, there's not a lot of adhesion. So there's an optimal range of where you want that coating to dryer. You don't have a lot of adhesion. And if you're riding right on top of a hard, heavy coating, there's not a lot of adhesion. So there's an optimal range of where you want that coating to stick the sheet to the dryer, and that's ultimately going to drive your quality. So this is just showing that obviously you're sticking it to the dryer, so it's impacting the tip all the time, and you're getting a nice fine crepe. And then obviously as you lose adhesion, it doesn't quite get to the tip each time, and you get a coarser crepe, which lowers your quality, especially softness. And then we have the blade and pocket influence itself. So, and this influences coating, but it also influences that impact. So this is obviously a very commonly known and obviously researched and understood principle, where that open pocket, the sheet exits the pocket easier, which is a top left diagram. You get a fine crepe, lower caliper, less tensile degradation. So that impact is easier. Often what you do at facial, very open pocket, trying to get a nice fine crepe. You can have a closed pocket, obviously as either through your application angle or your blade itself. So you get the bulkier sheet, and it's either through coarse crepe or explosion. And obviously the impact at the tip's going to be different. Then we spoke about how the actual material can affect this, so the hardness and how wear resistant it is, as well as the geometry of the actual blade tip. It's going to influence how you get into the coating. So that's going to affect the adhesion and from the previous slide, as well as what's happening at the tip impact. So if you look at this, the hard, sharp blade example at the bottom, it's going to could strip right back. Top is showing sliding wear, where the blade's obviously worn already, and it's not controlling the coating, starts right on top, so it's changing where it's going to be, and the middle sort of showing optimal. You're getting into the coating and sliding in it. And then the last one, just related to the geometry, and that is just showing a new blade and an older blade. This is obviously a soft material, potentially steel, where there's impact wear, and what that does is it closes the pocket. So you can see that the sheet is going to get coarser, and it's going to change that impact. And all these things we believe you can pick up to some degree with vibration. So historically, vibration's been used probably for about 20 years now, but it's been largely used to minimize Yankee damage, so to avoid chatter. So everybody's looking at that's the number one reason to use it, and it still is, and it's a valid reason, and that's pretty much where a lot of our uses come with it. And it's been used in this sort of thing when you monitor the vibration intensities, and at a certain level, operators or production are known to change the blade at that time before the coating gets too hard and chattery, so to avoid getting chatter into the actual Yankee surface. And then over time, that whole level might go up, and it tells production personnel when they might need to do a surface intervention like a sanding and that, because your base coat started to get too hard and chattery. But we believe it can be used as a tool more for productivity and quality as well. So generally, there's an accepted understanding of the different frequency indications from the vibration. So there's a 0 to 20,000 hertz of frequency, and generally the belief is the lower frequency gives you an indication of edge buildup, and the higher frequency gives you an indication of hard coating. And then there's that mid-range frequency sort of where it's a softer interface, and there's a potential thought that that's actually where you sort of indicating some form of creping energy related to good creping. So this can be broken out into the different bands and through the spectrum, and you can trend that so you can understand where you are in the layer. It's trying to help you sort of see where you are. So we believe if you measure it and evaluate it in a different way than just looking at the peaks and valleys, you can understand what you should do for better productivity and quality. The best way to do that is with case examples to show you how this works. So the first one is just one that somebody did use the vibration to make some coating adjustments. The blue line is when they started making the intervention. The blue dotted line is a light line with coating. They started to drop the add-on of the adhesive, and as you can see, the vibration trends in yellow started to come down and stabilize lower. And this also corresponded to better stretch and less breaks. So they were obviously too hard. So if you look at, they were obviously, the coating was too hard, the blade couldn't doctor it, it was riding on the top, and they were getting those some breaks and poor stretch. As they got further into the coating, because they softened it by having less base coat, they could get a better stretch, so they got into that adherent layer. So it's not just all about protection, you can also use it for quality. This is another one. As I said, coating is not just what you spray on the dryer. Sometimes what comes forward can affect the coating. So in this two cases, A and B, both showing white water variation. First one is they had crofter issues, so a lot more fines came forward to the dryer, and the coating hardened up. The second one, they had a pH wet end went up significantly, and the coating hardened up because it was a cross-linking coating. So in both cases, they had poorer quality and started having some breaks over that period. And this showed the same sort of thing. Those periods obviously corresponded to where that base coat started to harden up. The blade couldn't get into it, started right on top, started to get some probably bypassing and just general, and that was picked up through the vibration. Whereas normally during the other periods, it was obviously right in more optimal range in the coating. This is a more interesting one from a blade supply perspective. This is just showing the creping and the cleaning vibration spectrum. The steel period, tungsten carbide, which is the hardest blade, and the chromium carbide, not quite as hard as the tungsten. And then the cleaning blades were all steel, but it's just showing the time period. The creping was different materials. As you can see, the steel had a very high vibration on the creper blade and the cleaner. Tungsten carbide dropped the creping, but not the cleaner. Cleaner actually went up. And the chromium carbide, we managed to get an optimal level on both. And the thought process around what happened here is that tungsten carbide, as I said, depending on the hardness and the sharpness, it can really, a blade can really affect the coating. And in this case, we believe it went right through to the really hard base layer that steel cleaner couldn't do anything with. It sort of rode on top and started getting a chattery appearance and high vibration. Whereas the chromium carbide, also sharp, hard blade, but not to the same degree, left a little bit on the dryer that the steel blade could actually penetrate into and work within. So you could see that tip was showing at the cleaning blade, the vibration. This case was actually the reason I thought of doing this presentation and this article all we changed on this was the blade extension of, so I think by 5 millimeters, both using the exact same type of blade. It was and this in terms of material and geometry, tip geometry. So we moved it by 5 millimeters. And during that second period, the actual softness and bulk was better, so it showed better creping. And how this happened is it's picked up in the medium frequency of vibration. Total vibration was the same, but the medium frequency vibration picked up and the high frequency of vibration dropped down. And if you can see on the waterfall graph, it shifted. That's just the same thing. During the time scale, blue is where they changed the blade to the highest stick-out blade. And what we believe happened here is, with the previous extension, more aggressive, so it gets really into the coating, was running fine, but obviously was getting into that harder layer, right? So you had more high-frequency vibration, and with the increased extension, you didn't quite get in as heavily, so it wasn't as aggressive, but all other geometry stayed the same, and you actually ended up with better bulk and with better softness because you're in that adherent layer. So that was a very interesting case just by monitoring the frequencies that we could work out what was happening at the blade tip. This is a more standard, this I used actually somebody else's vibration system while we were running a trial. I just picked it up, and it just shows the two periods where we ran ceramic, different times of the trial. We ran one day, then later in the day. Just showed lower overall vibration, and at the same time we got better softness. And what you could see from that is we had a finer crepe with the ceramic, obviously a coarser crepe with the steel, a lot of up and down vibration. And when we did check the blade afterwards, we saw the impact wear and the high sliding wear on the steel. So obviously it wasn't getting into the coating as much, riding on top, and you had the impact wear changing the pocket. So you're changing that tip impact, whereas the ceramic stayed very sharp and managed to keep doctoring it. So once again, just to demonstrate what we believe is happening from that vibration, the ceramics getting into the area where you can get the good adhesion, keep the fine crepe. Steel obviously couldn't manage the coating, and obviously we've had the coarse crepe because of that, as well as because of the impact wear, because you closed the pocket. So we're seeing those impacts on the vibration. So in summary, vibration can provide key insights to what's happening at the blade. As I said, it's not only as a tool for Yankee protection, but you can use it to better understand what is happening at the blade tip, what's happening with the sheet impact, especially related to the coating, and what adjustments either affecting or can be made for better productivity and quality. Thank you very much.
Okay, thank you very much. Thank you for keeping your times. Okay, we have it's now for questions. Is there any questions from the people around? It would be nice to have some questions to put these things moving a little bit more. Okay. There is one question there.
Thank you for the presentations. My name is Tan Trung with Fitner, Voith Company. A few questions here. On the first paper for you, Carlos, with regards to the imaging, have you considered the use of hyperspectral imaging as a way to actually get these images, whether with drones, flyby, or with aircraft, instead of using just the actual satellite images itself? Because hyperspectral imaging would give you a lot more data on the crown tops and so forth.
Hello. Hello. Thank you for the question. The idea with this project was to try to find a way to check it remotely. So, as I said, most of those holdings are very small, about 2 hectares or lower, and it isn't financially available to those owners to get the drone service or to do those kinds of monitorings. Also, when you do drone flights, you get a few samples here, a few samples next year maybe, and with the satellite time series, you get an image every 5 days. And we can get automatically the detection of those differences. As for the spectral bands we used, the vegetation index, the NDVI. So it's mostly using the red bands and the infrared, the near infrared, to detect the chlorophyll. Yeah. So I don't know if I answered your question.
Thank you for that.
Yeah, thank you.
A second question. I'm not sure if this time. Second question for Juha. With regards to your models, how do you validate this? You're talking about GRAMMAGE, you're talking about fillers and so on, and all these models are calculated. How's the data being fed back to validate in your models?
Yeah, thank you for the question. And this is one of the reasons why I gave you the background of my mind. So I'm a chemical engineering, so clearly we have a team that is working data crunching and data engineering. So unfortunately, I'm not able to give you a very precise answer on that one, but maybe a good explanation is that we have been working with this technology, what we are using already like 8 years. We have several models for different kind of predictions. We are clearly using different kind of technologies and techniques in the modeling part, and we have been able to kind of during those 8 years to look and find a way how we can pretty accurately do the predictions. We are never going to be like 100% on the level because there's a lot of, let's say, variations that cause kind of the prediction to be, well, it's a good enough, but it's not really like accurate. There's also human error when you are doing kind of the lab measurements, and our system always auto-tune itself. So it's using this kind of system that after each lab measurement, it picks up the correct tags to be used for the next predictions until the next lab measurements comes, and then there's a variety of different kind of models and picks the most correct one that gives you the accuracy. So unfortunately, I'm not able to give you scientific detailed answer to your question, but I hope this is good enough. Thank you.
Yeah, I appreciate that. I just want to make sure that the models are not fed with something else that's completely...
Yeah. So our models, we don't need to do retraining. So sometimes you might hear that a retraining is required maybe once a month or something like that. So like I said, the technique that what we are using is there is a little bit more explanations or scientific explanation on the paper that we provided, and I believe that it is available in either in the website or in the app. So maybe there is a little bit more information, but like I said, we don't need to do the retraining. The model auto-tune itself after each lab measurement is come and it picks up from the QCS.
Thank you. Maybe one more question for Grant. You mentioned with regards to the idea that the results are essentially you're doing softness as an indication of the final improvement. Are you doing the softness by hand feel, or how is that done to validate that it's actually a softer product that's coming out?
Yeah, in most of the cases, it's with TSA, so it's so it's not something we necessarily done. It's we getting the feedback from the customer. Sometimes it's a panel, but it all depends. I think the one case was both. Because they had both. So yeah, all right.
Okay.
See where this goes.
More questions?
Okay, is it on? Yes, okay. Thank you. My question is also about validation for the control system. I was wondering if you could tell us more about the validation for recycled pulp or paper when fibers are recycled or coated, if this has been validated for this kind of mill.
Yeah, thanks for the questions. We do have models available for different kind of predictions for recycled fiber using packaging board, kraft liners, tissue. So unfortunately, time was limited, and during the slide I was showing last, there was a mention of several kind of models that we have been working with. Altogether, we have a solid list of customers that are using this globally, this system, different models, different predictions, clear kind of roadmap for next actions. What still are kind of missing is the wastewater treatment side, but there is a project starting in a couple of months where we would like to do some sort of evaluation if the model would be usable on that side, and then the next approach would be on the pulping side. So at the moment, these are the ones or applications where we still are looking a little bit ahead and into the future. Thank you.
There is time for one question more, if there is any from the room. Okay.
Hello, good morning. Hello once again. I'm Ricardo Mendes from the SMIT paper Vienna. My question is for Juha. It's about the artificial intelligence. If these AI models is supported by the instrumentation. If there is any problem with 1 or 2 or 3 tags, for instance, does the system keep reading and controlling? Does it give an alarm for the operation to be aware of that problem? How the operation can handle this?
Yeah.
Or if the whole model is off, if any instrumentation is down?
Okay, excellent question. First of all, the model understand if there is any kind of frozen tags or dead tags that we have selected and there's like no movement, it doesn't change, so it automatically takes those away from the modeling, so it doesn't use any more of the dead and frozen tags. On top of the prediction and control, our user interface is providing a feature called root cause analysis. So what it pretty much does is what kind of centerlining service is doing. So all the tags that we are utilizing and pulling from the customer system, so it creates a kind of historical centerline value. So showing what is the typical variation limits on based on historical values on that crate that the customer is running, and it listed top 5 or top 10 of those tags that are really out of the center line. So together with the prediction and control, this tool, this root cause analyzer, is kind of a tool for engineers to understand if there are some tags that are really out of the typical area based on historical value. So it does provide some gaps in the process, if there is any of those, and identifies, highlights, and this can be used for, if there is something happening in the process, you might have a quick look on the user interface that what's going, is there any tags that we are utilizing has some weird values. And then of course the system, like I explained, if there is totally dead or frozen, our model doesn't use those in calculation at all. Thank you.
Okay, thank you. It's time now to end this session. Thank you very much for your participation. Thank you very much for your presentations. I think that you deserve